Okay, so for problem number 69, 69 is an interesting problem. I'll read it out loud. It says there's an asteroid belt that lives between Jupiter and Mars. So let's kind of get this in perspective. We have the sun. It's shining rays of light, making us feel warm and fuzzy. And we love the sun because it provides all the energy for our solar system. Okay? And then somewhere way over here, there's Mars. All right, there's Mars. Right? And then Jupiter is like a lot bigger. And it says that there's a bunch of asteroids in between them. And it's an asteroid belt. Okay? Now, the asteroid belt takes 5 years to orbit the sun. Okay? Alright, so let me read it right out of the textbook. I'm kind of jumping ahead. It says, the asteroid belt that lies between Mars and Jupiter may be the debris of a planet that broke apart or that was not able to form as a result of Jupiter's strong gravitation. An average asteroid has a period of about 5 years. So period, remember, period is the time it takes to complete one revolution or one orbit, right? Here's the question. Approximately how far from the sun would this fifth planet have been? So if this would have been a planet, in other words, if we could have put this all together and made a planet, if all that little debris would have been a planet, it would have been about 5 years for a period. How far away from the sun would it be? Well, we know the period is a time. What is the relationship between time and the distance? The period, let me rephrase that. What's the relationship between the period, and this is Kepler's law. So go and look. Go and look on page 257, and this is technically Kepler's third law. So to solve this problem, we're going to use Kepler's third law. And my smartboard isn't cooperating today, obviously, but that's okay. And that law is this, the relationship between the period squared is equal to k times the distance cubed. Now Kepler's constant, as written on page 257, this has to do with our solar system. It depends on the mass of the object orbited. For objects orbiting the sun, the k value is about 2.97 times 10 to the negative 19 seconds squared meters cubed. Okay? What are we solving for? Well, I've got t, I've got k, and this thing right here is r. Do you guys have that all written down? So we went through, we read the problem, we drew a picture, we listed all the stuff that we knew. There's something that we don't know. What we don't know is what they're asking us is what is the distance. We use the variable r because it's technically like the radius of the circular path, right? And then we found an equation that worked. Kepler's third law. and it's called the law of periods, right? So Kepler's third law, the law of periods, is the mathematical relationship between the period squared, which is equal to his constant times the distance cubed. So I want to solve for r. So I'm going to start here. I'm going to say the period squared is equal to Kepler's constant times the distance cubed. I want to get r by itself. Divide both sides by k. So I get t squared over k is equal to r cubed, right? Now what? Yes?
You get rid of the superscript?
Yeah, so I could, there's a lot of ways you could do it, but I'm going to raise this to the 1/3 power. Now when I raise that to the 1/3 power, whatever I do on the right-hand side, I have to do on the left-hand side. But what that does is, remember this rule? You multiply those two numbers. What's 1/3 of 3? 1. So that leaves me with r, right? So the mathematical relationship is t squared over k raised to the 1/3 power, right? That's how I find the distance, algebraically speaking. You guys with me so far? Can I go to the next slide? All right. So now what we're going to do is we're going to plug in the numbers and see what we get. So I'm going to plug in for t. We said that period, oh, wait a minute. Oh, shoot. What is our unit of measure for time? Seconds. What do we have? Years. Oh, jeez. So before I can even get started, what do we have to do?
Convert.
We have to convert. So let's figure out what 5 years is in seconds. So I've got 5 years. How many days are in a year? That's not how many days there are in a year. There's 365 roughly. Right? Roughly. Okay. How many hours in a day? 24. I think what you guys, somebody in the back shouted out a really big number. I think you already did all the stuff. But let me show you where those numbers come from, okay? All right. So 1 day is 24 hours. So then I need to cancel my hours. So 1 hour is equal to 60 minutes. And 60 minutes, 1 minute is equal to 60 seconds. Now what I've done is my minutes cancel, my hours cancel, my days cancel, and my years cancel. So on my calculator I need to do 5 times 365 times 24 times 60 times 60. Okay, you guys ready? 5 times 365 times 24 times 60 times 60. Okay. That's a big number, isn't it? Now, you know what that is? That's the same as 1.58 times 10 to the 8. So I'm gonna approximate and say that t is approximately 1.58 times 10 to the 8 seconds. That's okay, we're just approximating. And we gotta approximate. Now, normally Mr. Adams would do this. If I was doing research in the summertime, like I normally do, I wouldn't round here. But your textbook does it because you guys are in high school and they want to try and keep things kind of simple. Okay? So that's what that is approximately. So now I've got to plug that into my formula. So we said that r was equal to t squared, right, all over k raised to the 1/3. Oh boy, that's a big number. So I'm going to have 1.58 times 10 to the 8 squared all over k, which was, what was that number again? Man, I forgot it. It was 2.94 times 10 to the negative 19, right? And then all of this raised to the 1/3. Is that right? Was it, yeah, that's what, or it was 9/7, wasn't it? The textbook used 3. should probably just use what the textbook used. Yeah, 9.7. So let me just use what the textbook used, because that will give you the exact answer in the back of the book. So what the textbook did is they said, look, that's so close. Let's just call that 3. All right. You guys ready? Plug it in the calculator. Okay, in parentheses, 1.58 second, comma, e to the 8th, right? That's going to be squared, right?
Yeah.
Divided by 3 e to the negative 19. Now I want to show you guys a little trick here. When I square this e to the 8, that's really 2 times 8, so it'd be 10 to the 16th power on the top. Then I've got 10 to the negative 19 on the bottom. Now when I have a negative exponent on the bottom, how do I make it positive? Put it on the top. So what's 16 plus 19? Oh, it hurts. 35, right? Yeah. I wish you guys could see your faces. You're like, carry the 1. Okay, so it's 35. So I should have something raised to about the 35 or the 34. Okay? So Mr. Adams is kind of, if I would have got something really bizarre, I entered it in properly. But I need to take that number and do what? Raise it to the 1/3. So I'm going to, if I just hit an enter, it'll automatically take the answer and raise it to the 1 divided by 3. And I get 4.365 to the 11th power. So this is about 4.4 times 10 to the 11th meters. And that's what it says in the back of the book. So what do we figure out? Yeah, what we figured out is that was the original question, how far away would this make-believe planet be? Well, it would be about 4.4 times 10 to the 11th meters away from the sun. And that's from the center of the sun to the center of the planet.